This is Module 15, Lecture Notes 30. Wow, we are getting really close to the end of this course. So today we're just going to go through a few more details that I wanted to walk you through in the equilibrium chapter. And so you'll read through this stuff in your book before class, but I do want to go through it in detail so that you really understand what the book is saying and how to do some example problems together. So last week we talked about calculating an equilibrium constant. Remember, that was K. And we said that it's helpful to know what the K value is for a reaction because we can know whether or not the reaction has reached equilibrium. Okay, so we just learned to calculate that for some general reactions. Okay, in this section here, I'm going to give you a few more rules about K that we didn't talk about last week. It says that when a solid appears in the reaction, we do not use it to calculate the equilibrium constant. And same thing for a liquid. If you see a liquid, it is not part of your K value. And the reason for that is in a reaction, the concentrations of solids and liquids does not change. And so it doesn't affect the equilibrium at a certain temperature. Okay, so let's practice writing the equilibrium constant for a few reactions that have solids and liquids in them. Okay, let's look at this first one together. So you'll see that I've put the state symbols for what state of matter each of your reactants and products are in. Aqueous is a solution. Those will be included. But a solid, you can technically now ignore when calculating K. Okay, so all I want us to do here is just write what the equation for K would be. Do you remember what goes on top? You're always going to put your products on top. So you would have the concentration of NaCl. Don't forget to put the 2 for the exponent, which comes from the coefficient. And then on the bottom, you're going to put your reactants. The concentration of sodium hydroxide squared and the concentration of magnesium chloride. And since there's no coefficient out in front, you can just leave it or you can put a 1. So this would be a full equation to calculate the equilibrium constant, ignoring the solid in your reaction. I'd like you to try to set up this second one. For the second one, I was able to eliminate the solid and the liquid because those are not part of the equilibrium constant. And so when I do products over reactants, I have these two. And I accidentally went ahead and drew my line, but I don't really need it because you're just going to multiply the concentration of lithium hydroxide squared times the concentration of hydrogen gas. Then you won't even have a denominator because the reactants are not part of this equilibrium constant. Okay, so you'll have a few like that on your homework to practice. Okay, in this next section, we're going to do a couple problems where we really talk about why this K value is important. It's always good to know why we're calculating something and what it is telling us. So remember that K can be used to tell us whether or not our reaction is done reacting, basically, or whether it's at an equilibrium state where the reactants and the products are forming at the same rate. If it's not at equilibrium, now we will know what it needs to do in order to get there. Does it need to make more products or more reactants? Okay, so let's jump into this problem and see how this works. It says the equilibrium constant for this reaction at a given temperature is 0.050. I want you to go ahead and outline that. We are going to save this piece of information for later. So I put use at the end. Okay, so we'll worry about that later, but the person doing this reaction knows that at this snapshot in time, the concentrations of her reactants and products are here, okay? And she wants to know is my reaction at equilibrium or not yet? And if it's not, which way does it need to shift? Towards products or reactants? So the first thing we want to do is write our equation for K. Okay, so here's my reaction. I don't have any solids or liquids, so I'm going to include everything that you see. So I'll have NO squared for my products on top, and then I'll have nitrogen gas and oxygen gas for my reactants on the bottom. Okay, so you're just going to take the values or the concentrations and plug those in, and let's get a value for K. All right, so here's what I calculated for K, 0.0002. If you didn't get that, take a look at the values that I plugged in, and then play around with how you're punching it in your calculator. But this is the number that you should come out with. What units should I have? This will be a good review from last week. On the top, I have molar squared, and on the bottom, I have molar times molar. Top, bottom, everything cancels out. So I actually don't have any units for K in this problem. Okay, so we have our K value. Now we want to compare it to what the equilibrium constant should be when the reaction has reached equilibrium. Okay, so we're going to be comparing these two numbers. I'm going to say that 0.0002 is less than the value given for the equilibrium constant. Okay, so you might want to write yourself a note that you're just going to compare your answer to the known value for equilibrium. And because the value that we got is less than our equilibrium, we know that we need to shift towards products. We haven't made quite enough products yet for this reaction to be considered finished at equilibrium. Okay, so you could write that out in a sentence. You could say because 0.0002 is less than the equilibrium constant at a certain temperature, we need to shift towards products. Okay, so I'm a person that likes written out rules that I can follow when doing problems on my homework, quizzes, tests, and so I've tried to do that for you here. So in general, if the number we get is equal to the equilibrium constant, well, that's perfect. The reaction is at equilibrium and you're not going to see a change. If the number we get is less than the equilibrium constant, like in our example, the reaction needs to shift towards the products. And then finally, if the number we get is more than the equilibrium constant, we know that we need to shift the reaction back towards the reactants. Okay, and so those are several rules that you can apply when doing these problems. On the back of your paper, we're going to look at Le Chatelier's principle. And this is the guy, this is Le Chatelier, and he was the first to study the effect that different stresses had on equilibrium reactions. And so these stressors could be anything like a change in concentration, a change in temperature, or a change in pressure. Okay, and we've talked about all of these things many times, and we know that they affect reactions because they affect how often collisions are happening. And so they have a large effect on reactions themselves. So let's look at these three things in more detail. For Le Chatelier's principle, the most important thing you need to know is that in an equilibrium reaction, when one of these things happens, the reaction is always going to shift in a way that relieves the stress and restores the equilibrium. So it's always going to try to bring the reaction back to equilibrium. Okay? So the first thing that we're going to look at is change in concentration. So let's say in this first reaction, I added some more nitrogen gas. More nitrogen is added. I want you to show that with an up arrow. If I increase the amount of reactants on this side, the reaction is going to try to counterbalance that. And in turn, it's going to create more product. And that makes sense. If I add more things to react, more product will be made. So for what happens, I would just write more product made. And since we have a product here that we can name, we could just say that more NH3 will be made. Okay, well, what if we do it the other way? What if I add more product? Well, remember these reactions go both directions. So if I have more product, my reaction will shift to counterbalance that, and more nitrogen and hydrogen will be made. So we would say that more reactant made. And our reactants would be N2 and H2. Okay, so I think you can see from those that it's always going to do the opposite of what you did to try to counterbalance. Okay, and then finally, let's practice with letter C. More carbon monoxide is added to the system. Well, that's on the product side. So to relieve that stress, my equilibrium needs to shift this way towards the reactants. So I will be making more CO and more H2. More reactants made. Okay, so you'll have a couple of those to practice on your homework. Let's look at another stress that we could add. Okay, so sometimes the pressure of your system will be affected. Okay, it says that when a system is subjected to increased pressure, it will shift away from the side with the largest number of gas molecules. Okay, so that's your rule of thumb. Shift away from the side with the most gas. Okay, and it's going to do that in order to relieve the increased pressure. Okay, so it says, which way will the reaction shift if pressure is increased? So I'm going to increase pressure, and we only have gas on the product side of the reaction. So we know we're going to be pushing back towards the reactants to try to relieve that pressure. Okay? And then lastly, the third stress that you could impose on a system would be changing temperature. When an equilibrium is subjected to increased temperature, it will shift away from the side that contains energy. Okay, so this is going to take us back to our unit that involved endo and exothermic reactions a little bit. So remember, the energy of a reaction, or the enthalpy, is written as delta H, and then you're given a value. And you need to know what that value is telling you. If that value is written as a positive number, it means the heat is written as a reactant. It's an endothermic reaction. If delta H is written as a negative number, the heat is written as a product. It's an exothermic reaction. So you need to know that piece in order to know which side of the reaction the heat is written on. Well, in this case, because it's a positive number, heat is a reactant. So we have water mixing with some heat, producing hydrogen gas and oxygen gas. And so now if I increase the temperature, I need to shift the reaction away from the side that contains energy. So we can say increased temperature is going to push the reaction towards the products. It's going to shift away from the side with heat. So those 3 things are important for you to practice, and then for you to know the general rule of thumb of how it's going to shift in order to relieve the stress. I did find a video on Le Chatelier's principle that I think goes over this on YouTube, and the guy includes some visuals for those of you that are really visual learners. And since I can't show that here in this format, I will make sure to include that link with the link to this lecture so that you can watch that if you wish. Thanks, guys.